Okay, continuing our energetics discussion, we're going to talk about calorimetry. Since we can't really know the exact enthalpy or heat content of reactants or products, we measure the change in enthalpy through calorimetry, or the measurement of heat flow. And we're going to look at an experimental setup for that in just a moment. But what do you remember? And you hopefully will remember, it hasn't been that long. How do you calculate the heat required to raise the temperature of a substance? Hopefully you remember that it is Q is equal to mc delta T. The mass times the heat capacity times the change in temperature. Delta T, remember, being the final temperature minus the initial temperature. Okay, the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius, because remember, delta T is the same for Kelvin as it is for Celsius. That's known as its heat capacity. What are those units for the heat capacity? They should be joules per gram Kelvin. That's hopefully what you remember, right? It's called the specific heat. Also, this just specific heat capacity. And there are some examples of some of heat capacity values. If you look at the heat capacity of water compared to most other substances, it is a lot higher. It has more heat capacity, more ability to absorb heat without changing the temperature very much, or to give off heat without changing the temperature very much. So now let's take a closer look at constant pressure calorimetry. Assume that there is an aqueous reaction in the styrofoam cup. I have 2 styrofoam cups nested, okay, together containing the reactants in solution. The reactants are in the inner cup. I have a thermometer to record the temperature. I have a glass stirrer, and I have a cork stopper sitting in the top. So what is the system? What are the surroundings? What is the pressure of the system? What kind of heat flow will there be? What is the purpose of the styrofoam? What type of system is that? If you remember from earlier conversations, the type of system can be open, closed, or isolated. Think about these questions for a minute. So what is the system? What is the surroundings? What is the purpose of the styrofoam? The styrofoam's purpose is to keep matter and energy inside the cup. Inside the cup. So I'm not having any exchange of energy or matter with the outside of the cup. So inside the cup I have water, and I have my reactants reacting, and that's how I'm going to draw them. Okay. So let's assume, because it's easier to think about it, if my aqueous reaction is going to be exothermic, what will happen? If my aqueous reaction is exothermic, I could expect heat to be released from the reaction to the water. Okay, if my reaction's going on here, I expect my heat to be released from the reactants into the water. Keeping this in mind, then, my system is the actual reaction or reactants. The surrounding is the water. The pressure of the system is atmospheric. What kind of heat flow will there be? Assuming that it is a exothermic, it will be from the reaction to the water. Purpose of the styrofoam is as an insulator to make this an isolated system. I answered that question. Hopefully this makes sense. If it does not, please ask questions. These are important concepts when determining system and surroundings and looking what's happening with that heat flow. It appears my computer. Okay, so constant pressure calorimetry. Because the specific heat for water is well known, that 4.184 joules per gram Kelvin, we can measure the delta H for this reaction with this equation. So Q is equal to M, this should be C, delta T, heat capacity of water. So that's equal to the heat released by the reaction. So Q is equal to actually the delta H of the reaction. It is also equal to the heat absorbed or given up by the water. Okay. So we can measure Q looking at the temperature change of the water, and then we can relate this Q back to the change in enthalpy for that reaction. So let's relate heat, temperature change, and heat capacity. How much heat is needed to warm 250 grams of water from 22 degrees Celsius to near its boiling point, 98 degrees Celsius? The specific heat of water is 4.18 joules per gram Kelvin. How much heat is needed? Well, I'm looking for Q. Q is equal to MC delta T. M in this problem is 250 grams of water. The C is 4.18 joules. I always write my joules funny. Joules Kelvin. And my delta T is equal to my final temperature minus my initial temperature, which is 98 degrees Celsius minus 22 degrees Celsius, which is, that's 76 degrees, right? Okay, cool. So, how much heat is needed to warm that? Well, the heat needed, Q, is equal to the 250 grams of water times 4.18 joules per gram Kelvin times the 76 degrees Celsius. And this will give me joules, grams cancel, Kelvin and Celsius cancel because I'm talking about a delta T. 250 times 4.18 times 76. I get 79,420. Sig figs, I should have 2, so I will report that as 79 kilojoules. So that's my answer for A. My answer for B, it says, what is the molar heat capacity? Well, if the heat capacity is 4.18 joules per gram Kelvin, if I multiply this by 18.02 grams in 1 mole, I will end up with the units joules per mole Kelvin, which is molar heat capacity. So 4.18 times 18.02, 73 point, if I looked at my calculator right, 75.32 joules per mole Kelvin. Okay. Large beds of rock are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules gram Kelvin. Calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees C. Large beds of rock. Quantity of heat absorbed. Again, hopefully, Q is equal to, this is problem A. Q is equal to MC delta T. I've got 50 kilograms of rock. The heat capacity of the rock is 0.82 joules per gram Kelvin, and I'm looking at a 12.0 degrees temperature change. Notice kilograms do not cancel with grams, so I need to have 1,000 grams in 1 kilogram. Now kilograms cancel with kilograms, grams with grams, Kelvin and delta C for delta T. I'm left with joules. So in the calculator, take 50 times 0.82 times 12 times 1,000. I get 492,000 joules. That's 2, 3 in my given. To be honest, I would accept as this answer either 490 kilojoules. I would also accept 492 kilojoules. I don't like taking heat capacities as my limiting for significant figures, but I don't know if that's exact number or if that was an experimental value. So I would accept both of those for the number of significant figures your answer should have. All right, so now B. What temperature change would these rocks undergo if they emitted 450 kilojoules of heat? Right, so now I'm going to solve this equation for delta T. Delta T is equal to Q divided by MC. They're going to undergo 450,000 joules is my Q. They have 50.0 kilograms of mass and 0.82 joules per gram Kelvin. I got joules to cancel. Kilograms don't cancel with grams, so I'm going to do 1,000 grams in 1 kilogram in my denominator. Now my grams cancel and my kilograms cancel. My units are 1 over Kelvin, so this will give me a temperature change in either Kelvin or degrees C because it's a delta T. Taking my calculator, 450,000 joules divided by 50 divided by 0.82 divided by 1,000 gives me a temperature change of 10.98. I'm going to record my answer because of this as 11 degrees Celsius. It's kind of a weird problem because they're awfully close to each other. But okay, there you go. We'll talk about bomb calorimetry the next screencast.